In 2018, the automatic speech recognition landscape was strictly segmented. Most research relied on traditional hidden Markov model and Gaussian mixture model pipelines. To build a functioning system, researchers had to piece together phonetic dictionaries, acoustic models, and complex decoding graphs. The industry standard for executing this was Kaldi. It standardized data formatting and used highly optimized C++ libraries to curate massive, messy audio datasets into reliable, ingestible data pipelines. But Kaldi's architecture was entirely rigid. When engineers wanted to test emerging end-to-end neural architectures, Kaldi's heavy reliance on complex finite state transducers and phonetic lexicons made rapid prototyping nearly impossible. At the exact same time, the broader deep learning community was abandoning static graphs entirely, moving aggressively toward dynamic Python-native frameworks like PyTorch and Chainer. Speech researchers were caught in an infrastructure gap. They had to choose between Kaldi's rigorous, battle-tested data handling and PyTorch's dynamic, flexible computation graphs. There was no native way to use both. This friction between data preparation and neural modeling stalled open-source speech research. The community required an architectural bridge to connect legacy data robustness with modern deep learning. ESPnet functions as a comprehensive open-source experiment factory. This diagram illustrates the core of that factory, the recipe. Instead of providing a generic transcription script, the toolkit offers standardized sequences of Bash and Python scripts explicitly tailored to process widely used public datasets. This architecture effectively decouples the messy reality of raw data curation from the advanced neural modeling logic. Researchers drop their audio into the pipeline, and the system handles the translations between the old formats and the new tensors. By deconstructing this recipe pipeline stage by stage, we can see exactly how the framework orchestrates complex multi-objective training and scales up to build billion-parameter foundation models. ESPnet eliminates the heavy glue code tax. It handles the pipeline plumbing so researchers can focus entirely on algorithmic logic. A standard ESPnet recipe execution begins at stage 0. The system downloads raw audio waveforms and their corresponding text transcripts. It immediately restructures these files into Kaldi-style manifest formats. Raw audio is mapped to transcriptions and speaker metadata across highly specific directories, primarily the wave.scp file. Rather than forcing users to rewrite their data, ESPnet's modern PyTorch data loaders are specifically programmed to parse and ingest these exact legacy manifest files. Moving into stage 1, the pipeline executes an on-the-fly transformation. It extracts 80-dimensional log-mel filter banks directly inside the neural layers, skipping the heavy offline processing steps of the past. This hybrid setup provides an immediate strategic advantage: perfect backwards compatibility with established speech datasets. Because the pre-processing formats are identical to those used a decade ago, you can run a state-of-the-art 2026 conformer model against a legacy 2014 Kaldi dataset, guaranteeing a mathematically fair baseline comparison. Locking the early data formatting stages to rigid legacy standards paradoxically freed researchers to iterate much faster on modern neural architectures. By stage 4, the data reaches the acoustic modeling core. Early end-to-end neural speech models struggled here due to severe instability during training. Pure attention-based models captured long-range context well, but they produced irregular sequence alignments. The models would frequently lose their place, causing them to arbitrarily skip or endlessly repeat words in the output. Connectionist temporal classification, or CTC models, offered the exact opposite profile. They maintained strict, forward-moving, monotonic sequence paths that locked audio frames tightly to characters. However, pure CTC networks process frames independently. They fail to capture deep, global semantic context across a sentence. ESPnet's major algorithmic contribution was mathematically fusing these two matrices into a unified multi-objective framework. They implemented a mechanism called joint decoding. This merges the probability spaces of both the CTC and attention models during the beam search phase. The CTC loss function mathematically prunes the unstable, hallucinatory paths generated by the attention mechanism, while the attention mechanism provides the linguistic context the CTC lacks. This stable training environment became the foundation that allowed the framework to easily integrate highly complex sequence encoders, like conformers and branchformers. This hybrid architecture stabilized end-to-end training. It enabled ESPnet models to reach and then exceed the word error rates of highly optimized Kaldi pipelines. While modeling logic defines the task, modern speech-language models require massive infrastructural scale to function. Attempting to load hundreds of billions of audio tokens into a standard multi-GPU setup triggers immediate out-of-memory errors. A few seconds of audio translates to thousands of individual frames, choking system memory. Older iterations of the framework utilized distributed data parallel training across discrete compute nodes, but scaling total batch sizes remained highly constrained by hardware limits. The ESPN3 architecture bypassed these limits by introducing the data organizer abstraction. This logic dynamically shards massive datasets, partitioning them across multiple nodes. It successfully decouples the global batch size from physical hardware limits. As a result, engineers can maintain over 80% GPU utilization while training 1.7 billion parameter foundation models across enterprise clusters. Operating at this scale requires extreme engineering rigor. For example, developers had to implement critical patches to chunk iterator padding logic, preventing silent batches of zero-value audio from passing through and destroying weeks of compute time. The data organizer architecture enables ESPnet to run enterprise-scale workloads. Independent researchers now have the computational efficiency required to challenge closed-source multimodal models on standard hardware. That infrastructure is no longer limited strictly to automatic speech recognition. Because the underlying recipe interfaces are heavily standardized, the exact same architectural flow applies to entirely different audio tasks. This diagram illustrates the unified ecosystem. The central recipe system executes parallel training pipelines for text-to-speech, speech translation, and neural audio codecs. Pass raw audio through these mirrored pipelines, and the system outputs different modalities: translated text, synthesized voices, or compressed audio logic. The long-term objective of this ecosystem is a unified spoken dialogue system. By running these models concurrently, virtual agents can natively process human interruption and emotional tone in real time. Mastering a single ESPnet recipe gives an engineer the technical framework to manipulate the entire multimodal audio ecosystem. However, that power comes with steep operational trade-offs. The toolkit carries massive technical debt from its Kaldi roots, forcing modern Python developers to navigate a complex labyrinth of legacy bash scripts and rigid directory formats. If a developer only needs to transcribe a podcast out of the box, consumer-grade APIs like OpenAI's Whisper are far superior. They prioritize plug-and-play simplicity over deep architectural configuration. To mitigate this high barrier to entry, the maintainers introduced ESPnet Easy. It acts as a pure Python native wrapper that drastically reduces the amount of boilerplate code required to run the pipeline. Engineers can now execute parameter-efficient fine-tuning, like low-rank adaptation, directly within an interactive Python notebook. Managed APIs are optimal for basic features, but for specialized engineering teams building the next generation of open-source speech foundation models, ESPN provides the underlying algorithmic sovereignty required to actually own the pipeline.